In this video, we want to do some questions that are related to real and imaginary parts of complex numbers, conjugate of complex numbers, and absolute of complex numbers. Prove that z is either real or pure imaginary number if and only if conjugate of z to the 2 equals z to the 2. First of all, note that this is if and only if question. So we want to prove that if z is real or pure imaginary, then conjugate of z to the 2 is equal to z to the 2. And also we want to prove the opposite of this, which is if this happens, then z is real or pure imaginary number. So here we have to prove two things basically. This is if and only if statement. When you have if and only if a statement, you have to prove two things. So we want to prove that if z is real or pure imaginary number, then z conjugate to the 2 is equal to z to the 2. And also we want to prove the opposite of this, which is this. If z conjugate to the 2 equals z to the 2, then we have to show that z is either a real number or it is a pure imaginary number. First, we prove this part, which is easier. We prove that if z is real or pure imaginary, then this happens. So first we prove this side of the statement. If z is real, we know that any complex number is in the form of x plus iy. But if z is real, so if z is real, then it means what? Then it means that z is only x and its imaginary part is 0. So z has only one part, and that part is the real part, and real part we show with x. And if z is x, what would be the conjugate of z? Then the conjugate of z, the conjugate of x is x itself. Because we know that the conjugate of a complex number, if we have x plus iy, its conjugate is x minus iy. But here z is only has a real part and its imaginary part is 0. So its conjugate is itself. So z is x, its conjugate is also x. So if z is x and its conjugate is also x, so it is obvious that z to the 2 is the same as z conjugate to the 2, and both of them are x to the 2. Because basically, as if you look at here, z and z conjugate are the same, they equal x. Now let's consider the other case. If z is pure imaginary number, so if z is pure imaginary number, then it means that z is iy. Because it is pure imaginary, the real part, which is x, is 0, so z can be represented in the form of iy. And if z is iy, what is z conjugate? Z conjugate is negative iy. Now let's raise both of these equations to the power of 2. What is z to the 2 from here? From here, z to the 2, from this, z to the 2 is I to the 2, y to the 2. But we know that I to the 2 is negative 1. So it equals negative y to the 2. But if you pay attention, z conjugate to the 2 would be negative iy to the 2, and this equals I squared y squared. But I squared is again negative 1, so it's negative y to the 2. Now compare these two. negative y to the 2, negative y to the 2. Z to the 2 is negative y to the 2. Z conjugate to the 2 is also negative y to the 2. So this shows that. So we conclude that Z to the 2 is equal to Z conjugate to the 2, and both of them are equal to negative y to the 2. So we prove that if Z is real, Z to the 2 and Z conjugate to the 2 are equal. And if Z is pure imaginary, also this happens. So we completed the proof of this side of the statement. If we suppose this, then this happens. We proved 1. Now we have to prove the other side of the statement, which I want to name it 2. So now we start from this, and we have to prove that Z is either real or pure imaginary number. So we suppose we say if Z to the 2 equals Z conjugate to the 2. Let's write this Z here and this Z conjugate in terms of real part and imaginary part. So we want to prove that. Let me repeat this again. If this happens, Z to the 2 equals Z conjugate to the 2, then Z is either real or pure imaginary. We know that always we suppose Z in the form of x plus I. We can suppose Z in this form. Now I want to replace this in this equation. Then Z to the 2 would be x plus iy to the 2. And Z conjugate would be x minus iy to the 2. So I replace this in Z, and because Z is this, Z conjugate would be x minus iy. Now let's simplify this. Let's raise both sides to the power of 2. X plus iy to the 2 is x plus iy times x plus iy. So this is basically x plus iy times x plus iy. If you multiply the brackets, it would be x to the 2, then xiy or I times xy. And if you multiply these two, and you have another I times xy, which means that we have 2ixy, and iy times iy would be I squared y squared, but I squared is negative 1. So at the end from this we have x2 plus 2ixy, or you can say 2xyi, and this is negative y to the 2. So left side is x2 minus y2 plus 2xyi. Keep this in your head. I want to erase this from here. So left side of this equation is x2 minus y2 plus 2xyi. So this is x2 minus y2 plus 2xyi. In a similar way, easily you can see that if you raise this bracket to the 2, it equals to x2 minus y2 minus 2xyi. By raising this bracket to the power of 2, which means that multiply the bracket by itself, you would get this. Now compare the left side and the right side. If we move everything one side, then x2 with x2 cancels. Negative y2 and negative y2 also cancels from both sides. What remains if we move everything to the left? By moving everything to the left, we get to this equation. 4xy I equals 0. Because x2 with x2, negative y2 and with negative y2 cancels. When we move these to the left, it becomes positive, so we have this. Now 4xy I is equal to 0. We know that I is a square root of negative 1. I is not a variable here. So from this, we can conclude that the coefficient of I should be 0, because 4xy I is equal to 0. So from this, immediately we conclude that 4xy is equal to 0. Let me tell you how we get to this. We know that I is not 0, so this should be 0 because this product is 0. So this means that 4xy is equal to 0. Because 4xy is 0, from this immediately we can conclude that either x is 0 or y is 0. Because 4xy is 0. So one of these components in this product should be 0. It can be either x or y. If x is 0, then it means that if x is 0, then it means what? It means that z, the pure imaginary number that we started here, if x is 0, then z is only pure imaginary number. And if y is 0, then this part of z is 0, so z equals x. And if z is equal to x, it means that z is a real number. So this completes the proof of the other side of the statement. We started, let's check the process. We started from this and we concluded that if this happens, then either x is 0 or y is 0. If x is 0, this means that the number is only pure imaginary. If y is 0, then it means that the number z is only a real number. And this completes the proof of this question. Let's move to the next question. Show that the equation absolute of or modulus of z minus z0, which z0 is a complex number, is just a complex number, equals r of a circle centered at z0 with radius r can be written in the following form. Let me remind you this. This equation is very famous in complex variables or complex numbers. This equation shows a circle centered at z0 and the r, which is here, shows the radius of that circle. Let me sketch this circle here for you to better understand what this equation basically is. This equation is equation of a circle. So when we sketch this, it should be a circle. We know that every circle has a center. The center of that circle is at z0. We know that z0 is a complex number, and a complex number lies in here. So z0 can be anywhere in this plane. For example, we suppose it to be here. So z0 is here. Attention, this is the center of our circle. R is the radius of the circle. So suppose this is R, then this would be the circle. So this equation, the graph of this equation is basically this circle here, and the radius of this circle is R, and its center, as you can see, is z0. So keep this famous equation in your head. Whenever we talk about equation of a circle in complex variables, one way to show equation of a circle is this, and it is very, very famous. Absolute, or modulus of z minus z0. Remember again, z0 is the center of the circle, and r, which is in the other side of the equation, and always it is a non-zero, non-negative number, is the radius of the circle. For example, r can be 1, 2, and any real, positive real number. Now we want to prove that this equation can be written also in this form. Absolute or modulus of z to the 2 minus 2 real of z times z conjugate plus modulus of z0 to the 2 equals r to the 2. To convert or rewrite this given equation in that form, immediately the first thing that I notice is that in the given equation here we have r, but in this new form we won't have r to the 2. So I think that it makes sense to raise this equation to the power of 2, because we want to get from this given equation to this. In the new form we have r to the 2, so the only thing that comes to our mind is that to raise both sides to the 2 to make it at least a little similar. So we raise both sides of the given equation to the power of 2, and then we have this. Now the right side of the equation is exactly the same, but we have to work on this part to make it similar to this. Now I remember something. I remember this, that absolute or modulus of a complex number to the 2 is always equal to z times z conjugate. We use this important identity in complex variables a lot, and it's very useful for solving questions. Whenever we have absolute or modulus of a complex number to the 2, we can relate it to the conjugate by this equation. So absolute or modulus of z to the 2 is always z times z conjugate. This is a very famous and important identity. So here I want to use this important relation in complex numbers to convert this to this form. So let's continue. Instead of absolute of z minus z0 to the 2, I want to write it in this form. So we have z minus z0 times by the conjugate of z minus z0. So we use this relation that we know, and we rewrote this in this form. This part plays the role of z. Modulus of z to the 2 is z times z conjugate. So modulus of this to the 2 is this times by its conjugate. And of course this equals r to the 2. Now let's open this. We have z minus z0, and for this part we use one of the properties of conjugate of a complex number. Conjugate of z minus z0 can be written as conjugate of z minus conjugate of z0. This is one of the properties of conjugate of a complex number. Now let's multiply the brackets by each other. Then we have z times z conjugate minus z0 conjugate minus z0 z conjugate, and then we have plus z0 z0 conjugate equals r to the 2. Now please pay attention. Again we want to use this, but in opposite way. Z times z conjugate is modulus of z to the 2. Z times z conjugate is modulus of z to the 2. So again, by using this important relation, we say this is modulus of z to the 2, and this is similar to this. Minus, I am going to factor a minus from these two terms, and then we have z0 conjugate plus z0 z conjugate. And for this part, again by using this relation, we can write it in the form of absolute or modulus of z0 to the 2 equals r to the 2. Now if you attention, so far we have written this in this form and this form. The only part that remains is to prove that this is this. So here we have to prove that this equals to 2 real of z times z0 conjugate. And it seems that I forgot to put z0 here in the question. Please pay attention. This should be z0, not z conjugate. Because if it is z conjugate, then it is modulus of z to the 2. It is z times z0 conjugate. So we want to prove that this expression in the bracket is equal to this. Let me prove something about this and its relation with this term here. The conjugate of this term is exactly this other term here. Let me prove this for you. And we want to use this fact. So we want to show that the conjugate of z0, the conjugate of this term, is basically this. Let me show you the reason. The conjugate of z0 conjugate is equal to conjugate of z times by z0 conjugate conjugate. So we separate the conjugate over each term. This is the property of conjugates. Now, this equals to z conjugate times by z0. Because z0 conjugate, if you conjugate a complex number twice, conjugate completely cancels. And we have the original number. And this is obvious that we can change the order of this and write this as z0 times by z conjugate. Because in multiplication, the order of writing the term doesn't matter. So, here, in this equation, based on this proof, we can replace this with this. So we can write this as modulus of z to the 2 minus z0 conjugate plus z0 conjugate. So I want to replace this term with this because these are equal, so I can do this here. Plus modulus of z0 to the 2 equals r to the 2. Now let me remind you another important fact here. And that fact is this: z plus z conjugate all over 2 is equal to real of z. Any complex number plus its conjugate divided by 2 is real of z, real part of the complex number. This is another important relation that you need to keep in your head. So z plus z conjugate divided by 2 is real of z. So if we have only z plus z conjugate without dividing by 2, we can multiply both sides by 2. Z plus z conjugate is 2 times real of z. So basically, we have this fact that z plus conjugate of z is 2 times real of z. We multiply both sides of this relation by 2. Now look at here. In this bracket, we have a complex number and its conjugate. This is conjugate of this term, added to each other. Based on this relation, we can replace this with 2 real of this complex number. So, finally, Based on this relation that I want to name it a star, based on a star, we can write this as modulus of z to the 2 minus 2 real of z0 conjugate plus modulus of z0 to the 2 equals r to the 2. And if you pay attention, this is exactly what we wanted to prove. Compare this equation with this. This is what we wanted to prove. So here we use two important facts. The first and the most important was this. The other fact that we used, this. And also, this was important, that this term is the conjugate of the other term. Suppose z is x plus iy. Show that the equation of the hyperbola x2 minus y2 equals 1 can be written in the form of z to the 2 plus conjugate of z to the 2 equals 2. So we have to start from this given equation and we have to try to write it in this given form. First of all, we note that we have to get rid of x and y. We don't like to have x and y in our equation. If you pay attention to here, we don't have any x and y. It is just z. So we have to think to a relation that relates x and y. Attention, z is related to x and y by this equation. Now we have to remember an identity that relates x and y to z. What is equation that relates x and y to z and its conjugate? Because in this given equation, in this new form here, we have z and z conjugate. Again, similar to the previous question, we remember this important relation. We remember this. We remember that x, or real part of a complex number, x, or real part of a complex number, is z plus conjugate of z divided by 2. Real of z is x. So this is basically real of z is equal to this. This is very famous relation. Real of z is x. And we have another relation similar to this for y, or imaginary part of a complex number. What is that relation, if you remember? That relation is this: y is equal to z minus conjugate of z over 2i. So we use these two relations, and in this way we can get rid of x and y. So we use relation 1 and relation 2. So by using 1 and 2, we replace x and y by these expressions. Then we have what? Then we have x to the 2. So x would be z plus conjugate of z over 2 to the 2 minus z minus conjugate of z all over 2i to the 2. It equals 1. Let's simplify this. 2 in the denominator raises to the power of 2, it's 4. In the bracket we have z to the 2 plus conjugate of z to the 2, and we have 2z conjugate. Don't forget this term. When you raise this to the 2, the first term raises to the 2, the second term raises to the 2, and always we have another term. Don't forget this term. That term is 2 times the product of these two terms. Remember this identity: a plus b to the 2 is a2, b2, 2ab. This is important identity. we use this here to simplify numerator. For the other bracket, in the denominator we have 2i to the 2. 2i to the 2 would be 2 to the 2, which is 4. And I to the 2 is negative 1, so this should be negative 4. But instead of writing negative 4 in the denominator, simply we can multiply this negative by this negative and make it easily positive to get rid of these negatives. So we put a plus here. So don't forget, this raises to the 2, this will be negative 4. This negative can be moved to here in the fraction. So negative times negative is positive. Now let's raise the numerator to the 2. Then we have z to the 2 plus z conjugate to the 2 minus 2z z conjugate. Because the between is minus, the last time is minus 2z z conjugate equals 1. The denominators are the same. We add numerators. z2 plus z2 is 2z to the 2. Z conjugate and z conjugate to the 2 would be 2z conjugate to the 2. And this term with this term cancels, and only we have these two terms in numerator equal 1. If we multiply both sides by 4 to get rid of denominator, then we have 2z to the 2 plus 2z conjugate to the 2 equals 4. And if we cancel the 2 from both sides, finally from this simply we have z to the 2 plus z conjugate to the 2 equals 2. And this is exactly what we wanted to prove here. So the critical thing here is to remember this and memorize these relations to prove this type of relations. I hope by watching this video you have learned how to use identities that already we know in complex variables and complex numbers, and how to use them to get the results. If you like this video, please subscribe in my channel, and see you in the next videos.